First, I think everybody knows me and I know everybody. Did you see the announcement of this seminar, right? And you see a picture of Agile very law and known. Okay? This is not my picture. This is a state, quantum state. Okay? What you see is not what you get. If you want to see the real one, you have to make a projection on the subspace of the Hilbert space, and you see me. Okay? So this is the quantum state. You can see this is the quantum state. It's not the. Okay, let me spend about 15 minutes or so to tell everything. In order to not forgetting, I write down here so I follow. Okay, first, we want to know why we are here. Okay, and what is all this project is all about. First of all, like Jumbo just said, you might be aware of the Center of CMU, Center of Computing Technology, and the COE of Economic. They are all interested in using quantum algorithm. So from now on, we call it QA. QA is not the room downstairs, okay? You have the QA rooms there. It's called what? Quantitative analysis, QA. And now for us, QA is quantum algorithm, okay? So we talk about QA, not the one downstairs. We want to use quantum algorithm to perform empirical research in econometrics, especially in finance, in investment science, to speed up optimization computation. This new research direction will be good for all PhD students and other researchers. New is better than old. Remember, from 1945 to 1975, what's that? That is when you have a computer. Starting with Alan Turing during the World War II, and end up 75 in Silicon Valley, San Jose, California, USA. With Apple, okay, that they have universal computing for everybody. After that, it's just an extension. But imagine that if you don't have a computer, what do you do? Can you do it by hand? Can you do documentation and put in thousands of numbers and do that by hand? No. So you are very happy and you take that for granted. Okay? But you forget one thing. You have your iPhone, it's not because of that. Not only iPhone, everything else is not because of that. It's because of you have the 1990, you have, this is the 30 years. Okay? From zero, that you have a computer, everything. That means we don't do that by hand. We ask engineer to build machine, and the machine will do that first. This is what you have the computer right now. The laptop, everything, all computation is only 30 years, from 45 to this. Now we have another 30 years. What's that? What we learned today. The new computing device. You would like to know it? You have to do it. Because otherwise, just think about if they do computer during this time, then you ignore. So this is exactly what we're doing today. 30 years already that they're talking about this. Okay? So it's about time to learn before it's too late. see the thing. Now, so we are here to learn about this computing device. So you should read that. This is the old stuff. This is the new stuff. Okay, this one is simply based on classical mechanics and electricity. This will be based on something else, whatever it is. I will explain from A to Z today. But we need to know that if we don't do that, we are not talking about this. This is what you try to learn. So this seminar, like I just said, I volunteer to do the following. Everything will be spelled out clearly in a minute. Every Wednesday, this month we have 4 Wednesdays. Everything about computing. And in November we have another 4 for how to apply quantum computing to econometric model. Just like the model that you know already, and also some new one. Okay, so after the seminar, if you want to know anything about practical how to use quantum computing, ask about it. If you want to know anything about hardware, ask Adam. He's the director of the center here. We have everybody here. And hopefully, when we have the next conference, we will have more experts to come. And they will give more specific lectures on this. But we need to start by knowing the language in order to study. So we will talking about quantum. So I just want to make sure that you don't stay anymore about the word quantum and what is it? One for all. So you're not talking about everybody when you talk about quantum, you say, oh, I don't have any idea. It looks like something very magic and difficult. I want one more time. If you not stay on this one. So here is what happened. Everything. Oh, by the way, don't need to take notes, okay? Because at the end of the seminar, I will have the handout, everything for you, so better than that. So try to focus and ask questions. Make sure that you get something, you have something to take home. That means you spend time here, after this, you get something clearly. Okay? So first of all, everything is made of particles. Second, every particle moves. Everything is made by the little particle. And if you don't move, you die. Think about it. If you are on a bicycle, if you want to stay on the bicycle, you have to move. And everything in our body, everything moves. If you don't move, you decay. So that is the real fact. Okay. So the question is, what makes things move? Okay, so what makes things move? Answer, by force. Okay. And there are 4 forces that you know. And there are 4 forces. One is gravity. Second, electromagnetic. Weak nuclear. And strong nuclear. That's all. And all the force in the nature. You should ask me. Gravity, what is the gravity? You know that. Okay? You know things from now. That's why we call it apple. Electromagnetic, just like you have the magnet. Right, sir. Weak nuclear. radiation. That's why you don't go next to a place where they make to make the radiation coming out very quick when it's a force by itself. The strongest one that we're talking about is they will keep you together. If you don't keep you, your body, nobody won't keep you together. The little thing keep you together. Okay? And that is called the strong, and that's the strongest one. Keep you together, otherwise we will fall apart. So that's the force. But the question is, the second one is, how the particle move? That make them move, and how they move. The answer will tell you what does that mean, quantum, and you understand quantum. If you go home after this class, anybody in the street asks you, what is quantum? You can explain nicely. You understand and you explain. They move. Particles move at discrete energy level. Understand or not? If I want everything, okay? Okay?
So would be
okay, here, okay, here is the hydrogen atom. The smallest one. What is it? One that's like that. This will be called the proton, right? And there's an electron will move around, just like the sun and the earth, okay? Like that. But this one has a positive charge, this one is negative charge. We call it positive, up to you. You can call anything you like. Okay? Like the fact that you can call north, south, or whatever, there are two different things. You can call plus or minus, negative or positive. It's just a convention. So this one is moving around. Okay? But it can do like this. Then you get here, and the thing disappears. It does not disappear. Because it disappears, then we are not here. Okay? So why? In other words, it moves like this. Then it jumps. That's what we call quantum leap. Remember? Jump, quantum leap. Jump to here, and then can jump here. Okay? And over here is the limit. Cannot come in. Come out. In other words, this is one level of energy. This is another level. This is another level. So they are not continuous. If they are like this, then it's continuous. And we hit here, and we have nothing left. It jumps like this. Okay? So we are not talking about computer science in this seminar. We're not talking about physics. Okay? So just in case that you are curious, if you're curious a little bit about quantum physics, go to my yard and go to the Asian bookstore on the third floor of my yard and buy a book like this. It's totally $200. Okay, $200. And this is for a book for mailbags, for anybody in the street, even if you don't have any class. And this you can read 1 hour in the evening before going to sleep. And you know that's all I'm talking about. I only learn from here, nothing else. Okay? I don't know physics, I don't know things, but I read this, I have a feel exactly what we do. So So discrete means quantum. In fact, this means how much? In Thai, this means how much, okay? So it's clear, huh? You talk about quantum computer, quantum mechanics, quantum physics, don't scale. It's just mechanics of things that discrete value, and we will see. Only discrete. It's not continuous. Classical one is continuous. Okay, it's just an approximation. So quantum means discrete, nothing fancy. Okay, just make sure that we're talking about quantum computing. So if anybody asks you, what is a quantum computing? Okay, of course you will say, we build a machine. The machine we build right now, the computer that you have. You need engineer to build a machine for you. Okay? You want to compute 5 plus 7. Okay? You don't want to do it by hand. So what you do? You have the machine. You have a machine here. You put in an input, and you will get out. You want to get out. Well, okay. So you put in here, because this is a machine. So you have to put in, let's say you use 3 qubits to represent number from 0 to 8. You make a coding. And you can only put in 0, 1, you cannot put in number 5. Because this machine, you can only do 2 things, on and on. Then you put in number. You write out the coding, what we see. This one internal, the bit 0, 1, you put in here, you put another one, you put it in, and in here, engineer will design for you through what we will talk about gate in a minute. It make operation, and come out 0, 1, and then you convert, and then you get another term. That is a classical computer based completely on classical physical mechanics. Now quantum computer, we are going to build another machine. And what we put it in is not a bit, we will see in a minute, we will put in a qubit. So inside, this is still the problem, because engineers have to build it first. Okay, this is the hardware part. And then will come out something that we get. So the quantum computing is based on, everything here is physics at this level. So this is based on quantum physics, that's all. Okay, rather than this one is Newton mechanics, we made quantum. So it's quantum simply means it's a mechanic of little thing, and little thing move at a discrete level. So quantum simply, don't worry about what is quantum. Quantum means how much or discrete. Okay, now, one thing, very important. When you write down the algorithm to do something, you cannot compute because you need to put in here. Engineer can do it for you or not. Okay. Because if you cannot, you can only get Oracle. You have to understand what is Oracle, because when you read book, they talk about that all the time. Oracle is magic. You write down an algorithm, but can you build a computer to execute your algorithm? If you don't know, it's not yet. You are talking about Oracle. Okay. So Oracle, on the paper that I can both recommended everybody to read, they talk about Oracle all the time. So at least I want to make sure that after today and next week, every time you look at everything about quantum computing, at least you understand what they're talking about. what is the language, including the math that I was talking about. Okay, now, one more thing. We were talking about in a minute, we're talking about classical computer and quantum computer. This is what, it doesn't mean that we are going to throw the classical computer everything away and replace it by the new one. This is a very good attitude of Einstein himself. When he talked about the new physics called theory of relativity, that means everything Newton said was wrong, but don't throw away. Build on it. Take advantage of this and make it better, but don't throw away and start from scratch. Here is the same thing. The classical computer, we will see in a minute. What is the mathematics? You need mathematics. You can see why. First of all, you have to describe what is going on. For example, how you represent a qubit. We'll see in a minute. Then the mathematics in here is simply Newton mechanics. And Newton mechanics is void. Just the void. Okay. Imagine if I throw a tennis ball. I throw a tennis ball. Then at a given time t, if you want to know where is the ball, so you only need 1 point. You need a point in R6, three dimensions for the position, and 3 dimensions for the velocity. Okay? Not the speed, the velocity. That means how fast in what direction. Okay? It's a vector. Okay? You need only 1 point to determine what is going on. But if you send in a photon, the light is small like this. You cannot see it. You need the mathematics to describe it. Okay? That's the main thing that's why we say, why we talk about math. It turned out we don't do mathematics, but they use mathematics for the language, and all we need to know is to understand what they write out. Okay? Now, so let me, so I think that is to answer these 2 questions. Right? So while we are here, we try to learn things to apply quantum computing. Now, first of all, the first thing, let me write out. Okay, here the classical computer, and you put in bit, let's say a 3-bit computer. Normally it's not 3 qubit, okay? It's million of bits, okay? But we will see how we do. So I have 2 qubits. So you only have 2 things. A bit you only have 0, 1, okay? You send in, if you can send in a string if you like a 0, 0, 0. That is to represent the number 0, and 0, 0, 1 to represent the number 1. 0, 0. Let's say 0, 1, 1 to represent number 2, and so forth. You can go on the way to number 7. With 3 bits, you can go and get number 7. Okay. Now, we will see if this is a quantum computer. In your register, the input coming in will be a qubit. Like that. During my last 2 seminars, is an object of the form alpha 0 plus beta 1, where alpha and beta are complex number such that equal 1. That is the qubit. Okay. You have to understand all that in 2 minutes completely what it is. Okay. That is the qubit. Rather than 0 and 1, you have that. Now, the first thing, we will explain everything. But the first thing is, you will say, why is complex? This is, I'm just what ask the other one, first of all, why is complex? Okay, so let me tell you this. What you set it in, what we set it in is, let's say, either an electron or easier a photon. Light, set in a light. This is what you are setting. And you want it to be something of this form, you have to do like a coding. Now, so you're talking about, let's say, photon. Let's say. The question is, what is a photon? Okay, answer. It is a wave. If you do not look at it, it is a particle if you look at it. I want to make sure that you understand that. It's very weird. It's true or not, nobody knows. But it works very well. You get your iPhone. You get the GPS. You cannot know what it is because you cannot see. The problem is we cannot see the thing, not like a white tennis ball that you can see. What does that mean if you look at it or you don't look at it? That exactly, when you set in the qubit, you don't know what it is. If you want to know it's a 1 or 0, looking at it is just a way of doing. You have to make a measurement. It's just like this is random. If I toss a coin, okay? I toss a coin, boom. When I cover it, I don't let you see. What is inside? Either head or tail, right? But you children don't see it. If you want to know what it is, you open it. You look. You don't do any measurement, and you know it's a head or tail. The situation for the qubit is different. You perform. Think about that. You perform a coin with a quantum coin. If you throw the quantum coin and you put it down, and it fall down and you go with it, what is inside? It's not head. And it's not tail. It's not head. It's not tail. If you want to know it's head or tail, you cannot just open it because you still cannot see. Find out a way to measure it. And when you measure, you will get and tell. That's what we mean by when you look at it or when you don't look at it. Okay? So when you don't look at it, why the wave? This is the main thing. Let me give you the answer for complex number first. Why complex number in quantum computing? Because complex number is to describe wave. You see, Fourier analysis. If you send in the signal, like you make radio wave, you want to decompose, so you can send. And how are you doing this? Fourier transform. Remember, this is in statistics we call it the characteristic function. W complex number. Because if we don't use complex number, you don't have the central limit theorem. The simplest one of statistics. Number one. So to decompose, so the wave is very easy to understand. Just go to any lake. Okay? Just go to any lake. And take a piece of rock and throw in the water. What do you see? Whatever of this. Throw another one. You can see this one and this one will cancel out. Oh, I'm sorry, we'll make it a bigger one. And this one will give zeros. The wave add up. Well, in order to represent the wave, you have to have this DOI complex number. So if you only ask number one, why complex number? Is you want to go to it. Because we send it is a wave. And in order to handle wave, we need complex number. And what it is, we will explain in a minute. Okay, and then if you want to know why it is a particle. So the qubit that you will send in is the simplest example of a quantum space or system. Okay, very simplest one. We are very lucky in computing because we only handle finite dimensional space. Because we have a 5 qubit computer, a 20 qubit computer, and things like that. Okay. You can see right away that if I have a 3 qubit, so how many things I can get? Okay, so 0, 1 to the 3. Okay, that you get it. But if you send in a qubit, how many? 1 qubit, 1 bit, you have 0 and 1. You can send in 0 and 1. Okay, put it over. Now 1 qubit is like this. How many of them? Billion. Billion of them. So it is the qubit has 2 phases. One is a wave and one is a particle. And why is a particle? One more thing before we will see that, okay? Because we use both of them. Because, in other words, when you send in, before you make the measurement, it is a wave. That means you know nothing. Where are you? Know nothing. But if you want to know if number 1 or number 0, you make a measurement. And when you make a measurement, it becomes a particle, not a wave anymore. It has 2 phases. So this one, why it is a wave? What happened is that Maxwell discovered that electricity, magnetic forces, of course they are waves. And how fast they move? they move exactly at the speed of light. That means 300,000 kilometers per second. Okay. But if it moves at that speed of light, it is light. Because nothing can move like that. Only light can move like that. That means light is electric wave. That means what makes the light? The photon. So photon makes light. And light is electric. So it's a wave. That's why the quantum qubit is a wave. Okay. Now why it is a particle? Think about it. We know what we're doing today with the solar energy, right? You try to make electricity by the solar sun, right? Okay. And what happened is this. Go ahead, take a piece of metal, the best one, and go to the sun. Look at a lot of sun heat. You hope that you have electricity running. What makes electricity running is that inside the metal there is electron inside. Okay, what is electricity? Electricity is meant when electrons move. Now we get electricity. So in order to get electricity, you have to move the electron inside. So how you move the electron inside? You have to hit them by something. So if you hit them by the light, it doesn't work. But sometimes it works. Why? Because think about you go in when it's raining. When it's raining. And when it's too raining and cold, what you get? You get the hail, right? The ice. But if a lot of little ice, a lot of them falling, it doesn't hurt you. But if one would make like this, it will hurt you. So it's not the number. It's not the number of things would come in, would knock out the electron, so you have electricity. But how big it is. How big it is, that means it has more force. What does that mean? If you look at this, this is the frequency. You can change the frequency. And you know the formula that I mentioned last time. Not E equal mc squared, right? That's not this one. The one is that makes your iPhone is E equal h nu. Remember? That's the formula. This is the Planck constant. We don't care. This is the frequency. So the frequency is energy. So if the frequency is high, the energy is high, that can knock the electron run. If it's not strong enough, electrons stay there. You don't have electricity. Okay? You need something strong. And that is discovered in 1905, and that's why Einstein got the Nobel Prize. So, the photoelectric thing. Okay? So that, for sure, that you understand the following thing. The qubit, I'm not talking about anything general. I'm just talking about something that we are going to use. The qubit, the input that you are going to put into your algorithm, had two phases. Wave, this is the wave. This is the form of the simplest way I will explain in a minute. This is the wave in the simplest form. Okay? We make a particle. That the number will come out. Okay? You put in, let's say you put in this, in the classical one. Think about this is the wave. Okay? But this represent the number 0. Okay? It's like we want this number 0. We have to do this. Okay? In order to get it out. But we really, like if I put it in 001, I really want the number 1. I put 1, I really want number 2 in my computation. So we should see why we have this 2 1 in here. Okay. That's the first thing. Okay, we will see. the first thing, when you do everything, you run into complex number. So make sure that you understand why complex number is there. The answer is very simple. We need complex number to study wave, because the qubit is a wave. Yes.
And okay, now wave is input and particle is input or output.
Huh?
The particle is input or output.
Both. We will go into that.
But wave is only input.
It does not the same thing, okay? The input will be, let's say 1 qubit system, okay? So that 1 qubit computer. Okay, that means you can only, in here, you input 1 qubit. Okay, we will do that in a minute. Okay? Suppose that you have a gate in here. We will do that in a minute. And they come out an output. Let's say a NOT gate. That means when you put it in, it will come out to be the other way around. Let's say we'll explain all that in a minute. Okay, so this is the qubit coming in, go through a NOT gate, and come out to be like this. First of all, you know nothing. This one you prepare. Just like you put in 1001, you have on your computer. Okay? When you put in, let's say, when you put number 5 on your, you want to 5 plus 7. Okay? So you put a button on number 5. The computer memorized already. When you put number 5, they will not put number 5 in the machine. They will put something like 000 that you called before. Okay? That come in. So you can prepare this. We are talking a little bit about hardware later on. Something called light polarization. Okay? You send in a light, whatever, and then you put a prism. Then the light will change. Depend on, and you do this, you get red color, blue color. You do different things, you get different things. Okay, that is one reason also that complex number have to be used, because angle we will turn things around. That's why you prepare. If you want to put in the alpha and the beta, we do that in a minute. So this is the to prepare. You put it in, the computer will give you this. You see nothing. You have to make the measures. That's the difference. In ordinary computer, it's very easy. You put in 002 and go through the gate. The gate is just Boolean logic, not or and it come out. And when it come out, it tell you, and you can see that is number 5, and the total is let's say 12. You get it. But here, and you get that for sure. Here, what is happening, we will see, is where this one you prepare. And you want something? No, come here. And you come out like this. This is the theory will tell you. But what does that mean, this? You want to know if it's a 0 or a 1. You make a measurement. The machine will do it for you. But the problem is, the outcome is random. And this is the probabilities. We will see in a minute. This is a complex number, we will call it amplitude. And this is the probabilities that if you make the measurement in here, if you make the measurement before, it will be the 0. And this is the probability of getting number 1. So it's a little more complicated. There's a uncertainty involved. So first, complex number. Okay. Number two, before I go in, the main reason we are studying is because we expect that is much faster. Can you tell me why it's faster? This is my example. Suppose I go on here. I just want to know who knows complex theory. Okay? So how I do that? I will ask one by one. I ask him, he say no. Then I ask him, he say no. Okay. So take me 35 questions. Okay. That classical computer. Now quantum. I ask one question for everybody. Who know? Who know complex variable? One question. Massive parallel computing. Okay. Just an example for you to see why quantum computing will be much faster. And we will talk about how you make it faster. But you should know the thing. It's exactly like ordinary computer, and this is what happened. What happened actually, the biggest problem in computing is this is the biggest problem in computer science. Ordinary real time and non-ordinary time, like exponential. Like if I have 10 person, okay? If I ask one person, how long it takes me to get the answer? N, okay? I ask one person, two person, three. Okay. Now, the first algorithm in the book will show people after that is rather than the order of n, they have order of square root of n. That's not bad. That's not bad at all. Think about n equal 10,000. Okay? And you need 10,000 questions to get something done. And can you bring it down to square root of 10,000? It's much faster. That is everything about, okay. Okay, two more things, then we will start. And after this, before I started, you think, just ask me, is there anything else you want to know? Spooky action and distance. Albert Einstein. Weird, very weird. Okay, understand? You will see everywhere in every book. By the way, one of the book that I will recommend, everyone have to get. You can read this for 1 hour at evening and you know everything. Okay, short book. We send it out for everybody. You should print it out. If you read it here, you don't understand. You have to take it out and do it 2 things. Before go to sleep, take 1 hour and read like a novel. Nicely read. Everything. Only 100 pages. You can learn in 1 hour. Okay. Try to believe that you can. You don't need any teacher. This is better than the best teacher. This is the book. I think that there are 3 books available in the center. There are 3 copies in the center. You can go there and take a copy or ask him to send for you the file. Okay.
I will send that now.
Yeah. Easy, but you have to print it out. Don't print from the computer. You have to print it out. First of all, do it 2 readings. Read it one night for fun, and then next morning, take a piece of paper and learn page by page. It's very easy and you get everything a taste of everything, both hardware and software. So, spooky means weird. Okay? Very strange. But this is the basic of quantum computing. And this is called entangled. The technical term is entanglement. This can be only one qubit system you don't have. You have to have a composite system. Actually, multiple qubit computer. Computer with you can set in like let's say qubit, let's say three qubit computer. What does that mean? That means you can set in 1 qubit at the same time. And the state inside is the superposition of all the three. When you have two, you have one and you don't have entanglement. What that means is this. Here is Chiang Mai. Here is Moscow. Far away, right? Very far, right? I do that. It affects something in Moscow right away, faster than the speed of light. That's something, action at a very far away distance. Einstein does not believe that. That's what he got spooky. He said, things like that will never happen. And that's why it makes computer faster. Because you save a lot. You save a lot of time. Because suppose that just like I will do it in a minute. Suppose that 1-1. Okay. You know that the whole thing is either 1-1 or something. This needs 2 qubit. So if you only measure the first qubit and get 1, you don't need to measure the second one because you know it's going to be 1. It is correlation in statistics in the quantum terms. In statistics, you have two variables, like interest rate and exchange rate. Okay, they are not independent; they are correlated. Maybe exchange rate will go up every time that the interest rate is go something. Okay, and we do that. So here is the same thing. There's a correlation between the two. If you know the correlation, then you only do this one. You know, right away. Faster than the speed of light, and that is impossible. Because the speed of light is the highest speed. How can it be that I can do this and right away? Because how long it take the light to go from here to Moscow? Okay, you can find out right away. Okay, 300,000 kilometers per second. It takes some time to go, not right away. Right away means faster than that. So how can it think like that? The problem is that you are not really sending anything. Don't forget information. If you know, okay, you know, but you are not. You know right away. If you know 1-1, you know the whole thing is 1-1, and you find out over here 1, then you know the other one is also 1. Okay. and so on. The example that they always do is the so-called Bob and Alice. A, B, okay? So let's call it Alice for the girl and Bob for the boy. Okay? So A, B. That's the example. Okay? So suppose that I have a pair of gloves, one for the right hand, one for the left hand. And I give one to Alice, I give the other one to Bob. But they don't know which one they get. But they know one is on the left hand, one is on the right hand. Okay? And then Alice stay in Chiang Mai and Bob go to Moscow. Tomorrow, Alice open and see, oh, Michael is on the left. So she knows right away that the one from Bob is on the right. Okay, that's called entanglement. And we will see entanglement is essential. State without entanglement, it has this property, but it's not in contradiction with Einstein. It doesn't mean that something travels faster than the speed of light. No, it's not. It doesn't mean that. Okay. So the problem we will see is how you have to create the entanglement in your algorithm. If you don't do that, it's not fast. Okay. We will. The last thing before I stop. Uncertainty. Okay. So you can see when you look at this, you have how many things. First of all, you worry about why we need complex number. The second thing you want to know why it will be faster. Okay. And number 3, what makes it faster? Entanglement. These are the 4 buzzwords. And the last thing is the quantum probability. Okay, this right here, the qubit coming in is of the form. I will tell what it is in a minute. Alpha and beta are complex numbers, such that the distance, let's say the modular square, is equal to 1. What does that mean? This means, look at the random variable, would have two values. The change for density, the density is alpha square. This is the beta square. So at the probability they have to add up to 1. So the question is, what is that? What is the qubit? First of all, this is called the amplitude. Because it's a wave. You see the wave? You see the wave? It looks like the amplitude. Then you can see the amplitude is complex number that is cannot be probability. Probability is the real number between 0 and 1. So the amplitude, because it's like if it's bigger, then it makes the wave bigger, so it's called amplitude. Everything is from wave mechanics 200 years ago, the classical mechanics. Okay. Now, why does, well, we will do that in a minute. Complex number means this is of the form x plus iy, and the conjugate is x minus yi. And the absolute value is the Pythagoras. The Pythagoras theorem. This one is number. Okay? And the square of it, the meaning is the probability to be when you measure you get up. Why is that? That is called Copenhagen interpretation. they use some apparatus to measure. Sometimes they get 0, sometimes they get 1, and it's completely random. There's nothing they can do about that. That what we call quantum mechanics is intrinsically random. When I toss a coin, I don't know head or tail. Why? Because I don't have enough information. If you tell me how you toss it, I take it from here. How far from here to here? What is the direction? What is the force that I toss it? If you give me everything, I can tell exactly. It's not random. I can tell you exactly it will be head or tail. So it's random because we don't have enough information. But it's not because it's random by itself. Every statistic is not random by itself. We don't have enough information. Intrinsic means even you have all information, you still cannot predict. By nature itself. And everything, you still cannot. That's what they call intrinsic random. So when it's random, they try to do experiment. Okay, let's go statistic. This one, let me measure 100 times and see how many times I get this, how many times I get this. It's about this. That in Denmark, Copenhagen, because that's the place where they invented quantum mechanics. Of course, there's a Iraq. So this is the interpretation, and it worked very well because you get your iPhone. True or not? It's more successful than anything else. If you build that for VDO, you get exactly what you have. So that's all, okay? So that's all that we need to have a picture about. So I want 5 minutes or more. Any question? Any question about this thing? Read the book and learn more out. But I everything I told you. I'm not an expert on anything. And you can. You really need this. What do you need? Because start from zero. If you're curious a little bit about how they make the iPhone for you, you go to my guy, go to the Asian bookstore and buy this one. 200 baht and read, enjoy it from zero. Okay? This guy is the best teacher. He has 3 books. If you want to know the concept, the first one is classical mechanics. From zero. What is the force? What is the energy? Okay? For layman. You can read in 1 hour and know everything. Second one is not this one. Second one is Einstein relativity. Easy, everybody can the way he did it. And this one, the last, combining classical relativity and quantum mechanics together in a little book. Okay, any question? Before I start at least few things. Anything new? Anything new? Is anything I miss? This is the reason the big picture of quantum before it. One thing is very important. You cannot run until you know how to walk. So be patient. Don't come here and say, I come here to tell me how to put a button. Not doing that. Okay? Not doing that. We want to be able to read quantum existed already. And then to read. You will see a minute on the symbol. It's just like this. Suppose that you want to learn something, but it's written in French. And you don't know French. So what you need? Learn French. That's all I'm doing. The French I'm learning is called mathematics. One more thing. If you go to the market fund, you ask them, what are the mathematics that you learn? They will tell you two things. We study real analysis and functional analysis. And if you ask them why, they will say, why not? That is the teacher teacher. The teacher does explain where the mathematics comes from and what from. Okay? It turns out mathematics is come from physics. And economic everything will follow physics 100%. Science first. Mathematics is just a language to do science. It's by itself means nothing. So why is real analysis, why it's functional? You can see right away. In classical mechanics, if you want to know where the position of my tennis ball when I throw it, you only need 1 point. And you need 1 point. You need 1 point, and you write out Newton's second law of motion. The force is equal to the mass times the acceleration. That's the second law of motion. Okay. Now, in order to, that's what he thinks. He do experiment, and he thinks that when he throw things, the force depends on how heavy it is and how you put it in. When you apply the force, things will go faster. But what does that mean, go faster? They change the speed. But what is the rate of change of speed? That's called acceleration. Okay, so that's what he feels, and we do experiment. The question is, how we apply that to build the airplane? You have to invent the mathematics for this. The mathematics have two things. Okay? So, first of all, derivative, differential calculus. That's what you call calculus. Okay? But how do you find out the trajectory actually? You have to do integration. You do two integration. Okay, what is that? This is derivative. So how do you get dt? Okay, so integrate, then you get this derivative. This is the second derivative. You take one integration, you get first derivative. You want actually one more. And that to build the airplane. So all this is mathematics is called real analysis. Okay? Now, what is the counterpart of this in quantum? We are not talking about a big object which has a mass m. We're talking about a tiny particle. It has a mass, but it doesn't follow this one. That's what I mentioned the other day. The counterpart of this is the Schrodinger equation. Everything in here. Okay. Explain in half page. Wave equation. complex partial differential equation. Doesn't matter what it is. But the problem is this. What is the solution of it? The solution of this is clear, okay? You get a trajectory. At this time, the position is here. My tennis ball goes like that. It's easy. You write down, and that's why we know that the sun here, and this is the earth. That's why we know the earth goes around the sun like that. This is one focus. Now, problem here, the solution here is not a point, it's a function. And that function is called the wave function. And that, the simple form is precisely this that I will explain now. That means the qubit. The qubit is the simplest solution of this one. So you can see this wave function. This wave function. If the function is not a point anymore. So this is, it doesn't give you the position. Okay? Here's a, when you solve this one, you have completely. This is called the phase space, which has the position and the momentum. The momentum means the mass times the velocity. Okay? This is the space like that. It's 6 dimensions. 3 for here, 6 for here is Euclidean 6. But this one is a function. A function dimension is infinite. That's why we will mention in a minute what is the Hubble space. It's not only infinite. This one is a function. But what is the meaning of that function? That's the problem. Here, when you get this, it's clear. What is that? At time t, my tennis is at this position, giving x1, x2, x3. And the speed at that time, when I hit the ball, is something and go into what direction. Everything is done. Here, this one gives you something like this. Okay? It doesn't tell you where you are. It only tells you that the probabilities that you are at this point is alpha squared. And the probability of this one is this one. So you don't get, you get the solution, but the solution is like you get a qubit. It gives you all the necessary probabilistic information. What is it? Random. But at least something that we will like very much in statistics. It gives you the distribution. The most difficulty in econometric is we formulate by random variable, but we don't have the distribution. Here, give you the distribution. So that is everything. So let me start from number 1. This is from the end up. Okay? This is from the end up. The first thing, complex number. Let me tell you a good news that you will like. We are talking about only computing, quantum computing only. I'm not talking about anything fancy. I'm not talking about quantum physics, only for quantum. Dimension is finite. Why I can go?
No, I lost something in the
Right.
in the wave functions. You mentioned that we need qubit, so we can understand that the qubit is equal.
The qubit is an example of the solution.
Yeah, so but the qubit is an input for us. So we
No, we're not talking about input and output. We're talking about quantum system.
so
What is quantum system in quantum computer?
and what is the role of the qubit? The role of qubit.
Just like the bit.
So the bit is the input.
Output too?
But okay.
It's just like the bit. It's just like the bit. exactly that bit. Here, okay, we do that in here. Width, okay? You have 0 or 1. Okay? This is 1 qubit. 2 qubit, you can have another one and you can have 0, 0, 1. Okay? That is a bit. Now qubit. Okay? How many of them? Billion. I will tell you what it is in a minute. All of them, for every possible alpha, complex number equal to 1. Okay, the set of all that. The dimension of this is infinite. Okay? So, when you solve Schrodinger equation, you get a wave function. For example, this is the wave function. Okay? This is the wave function. You know alpha, you know beta. Because in a system that you know everything, when you solve it, you don't get, you get a solution. And the solution is of this form. That means you get alpha equal, let's say, 0.1, and well, let's say some number like whatever, x plus iy, okay, and beta x prime y prime, okay. You can get two numbers.
So the alpha and beta is not parameters. It's just any number.
It's any complex number.
It's a complex number, but it's not a parameter.
What is the parameter here?
So I try to connect with the classical one. That if we want to find something like unknown things, we want to know the unknown parameters and that's the real number. But for in this case,
No, they are not parameter.
so it's totally different.
No, they are not parameter. They are not. Just think about qubit, a bit, just like a way to represent bit. Okay? For example, if you have a 2 qubit, then you have, let's say 3. Okay? Let's say you have 0, 0, 0, 0, 0, 1, whatever. Okay? Okay? 1, 1, 1. Have that to represent number 0 to number 7. Okay? Suppose that's it. So now if you have a 3 qubit computer. Around on 5 qubit. He's building a 5 qubit, okay? And we need 20 qubit. We need 20 qubit. So suppose you have 3 qubit. 3 qubit computer. Okay? So what does that mean? That your computer, we'll talk about that in a second. Where is that? I just show over here is state, phase space. Over here we will talk about state space. You see the difference? Here the space. In classical we got phase space. So in here you can input a 3 qubit. What does that mean? What does that mean? A 3 qubit. That means 1 qubit, we will do that in a minute, okay? Let's show you quick. 1 qubit, you are going, the state space of 1 qubit is C2, we do in a minute. Okay? C2 in a minute. And another one, we are going to do tensor products. So you get C4. Tensor product, you get C8. Attention, not 6. Okay. We will explain on that today and next week. But you can see that means you can have what is the input that you put in here? But with alpha 1 plus alpha 2 to alpha 8. What does that mean that we were talking about? These are the basic computational one in minute. But this is the long one, is the input. Okay? So this one is the input. So this is represent the state. The input is the state that you put it in. What you want is something else. We will talk about gate, quantum gate in here. Okay? You want to add, you want to multiply, or you want to do optimization. That is inside. And so when you get out, you will get out another one. Because you know what? You will see a minute. You put something in, something out. This is a transformation. Yes?
That one is 3 cubic, right?
This is the 3 cubic. Yeah. 3 cubic. Dimension is 8, not 6. Okay? We will go into that. It's not the Cartesian product. It's a tensor product. The tensor product is nothing else than canonical multiplication of matrices that you know. We will see. What I want to say quickly is this. This is the thing that you should enjoy. When we do quantum computing, we only need one simple mathematic, matrix theory, only, nothing else. We only know matrix, we don't only need matrix. And I will review that in a minute. Nothing. Only matrix. But if you want to do physics, quantum physics, then you need to learn more. Okay? So for us it's very simple. Because we only, if we focus on using quantum algorithm to speed up optimization in economics, that's what we want. We only need to understand a little bit of matrix in order to make the quantum algorithm. Nothing fancy. Only metric. So, to show that, let me just give you, so only need matrix. So please raise your head. Who does not know matrix? That means everybody knows. Okay? Everybody knows. So everybody will say the following. A matrix M is a table. Would have, let's say, a row. We write a row first. And column. Row first and column. So this is M by N matrix. What that means is you put number in here. Let's say A, J, K. Never use I, okay? Because the I will be used for complex number. Okay? Don't mix up. So here, but that really makes no sense. So let me tell you one thing is very important in computing is when I write things like this, I don't tell you what is one. Any coordinate system. So unless you have a matrix, only if you tell me what is the axis. You change the axis to get different thing. And the whole idea is this. You should enjoy what I'm right out here after that. Let me tell you. Okay. Okay. in 1945, Nikola Copernicus in 1543, Nikola Copernicus, I went to see his picture in Warsaw in Poland. Okay.
Oh,
Yeah. Okay.
I've seen that.
Yeah. He's the one who said the following: the earth go around the sun, not the sun around the earth. Okay. The Catholic said from the Bible that the earth is at the center of the universe. Everything go around. Okay. Until him, he just think that no, the sun is here and the earth is go around. Okay? But the question is, how? Okay? Not how. Because they don't understand that. He doesn't, there's no mechanic yet, okay? Mechanic, Newton is technique. Don't forget. Okay? There's no science yet. So how you know? You want to know where it is, not how. Okay? And how you do it? You make judgment. Okay? You can make judgment. Okay, here, and then later on here. So you end up with an equation like this. AJK, X3, or JK. Let's say it's in a plane, because that one on planet. It's a plane. Okay, everything is go on a plane. Okay? So, but they look at that. They can't tell. They can't tell how it looks like. But there's a guy very smart. He said, you can, this is called a quadratic, this is the quadratic form. Change that into a normal form. You can change that into only one. You can change it to this by a rotation of 45 degrees. And that gives you an ellipse. That's the equation of an ellipse. Okay. So, but when can you do it? If you write out this as a metric, that's the first time where the metric comes from and where. If this metric is symmetric. If this one, he just write out this table, and this is one is symmetric. That means transpose is symmetric. Then, so there, if the metric is symmetric, then this and this are the same. And where is it? These are eigenvalues of this matrix, and they are determined by the equation determinant of f minus lambda I equals 0. Beautiful. Everything comes from that. From that we have a linear algebra everything today. Only from that to figure out this is how the Earth is an ellipse around the sun. Everything is astronomy. Mathematics is invented for us to understand what is in the universe. Okay? So that's why the metric come out. Okay? You just change the coordinate. You can change the picture. You look at this. You draw this. Let's say in that coordinate. You don't see how it looks like, but you rotate it. If you change the coordinate, it comes out with this form. And when is that possible? If this one is symmetric. If it's symmetric, not only that it's possible, but you can find out the solution. What is this? These are eigenvalues. Okay, we will explain that. this is expression computing. So all we need is a matrix. So let me show that I can use matrix. Only I need is matrix to get for you complex number. You will write, okay, complex number is something like x plus iy with the funny thing like I squared equal minus 1, okay. It's not that. Okay, what happened? Here is the plane. Here is the real line, okay? And here is the plane. This plane, we call it R2. This we call Euclidean plane. 2 dimensional. And this is a subset of this one. So, what I'm doing, you will see, is exactly the same thing that we go from classical computer to quantum computer, and also from classical probability to quantum probability in the same process. Now, I want to say the real line is a subset of this one. Okay, that's correct. It's inside the big one. Now, if you have a vector, and let's fix coordinate like that, okay? So x mean here and y mean here. If you have a vector x, y in the plane, and if you have another one, then you multiply it. You cannot, because suppose you write this as a matrix. It's a 2 column, okay? Two row and 1 column. You multiply with this one. You cannot, okay? There's no matrix doesn't multiply like that. So matrix, if you have one like a n plus m, then you can multiply. If the other one is starting with m, let me, okay? You have to have something in common like this in order to multiply. You cannot multiply. So, if you want to say this plane is still itself, but you want to make that to be a complete plane. It's the same thing. But you can multiply, just like a number. Okay? You can multiply the number. If you write out vector, you cannot. But if you write out something else, you can. So here is what it is. Identification. This is what you call coding. If I have a number, I code it for any reason, sending it to some, I make that into that matrix. It's a bisection. If you have x, you can make this one. If you have a matrix like this, you can find out x. Okay. Now, if I have a pair x, y, what is in here? I represent it by bisection. If you give me x, y, I can make this one. If you look at the D1, you can find out what is x, what is y. Okay. But what is interesting is It is an isomorphism. What is that? It's a bisection, but preserving the algebraic property. On the real line, what you have? 3 operations at least, okay? You can add, you're going to multiply the number, and let's say you can divide. Now, if you have a matrix, what can you do? You can add 2 matrices, you can multiply 2 matrices, and you take inverse. The inverse of the matrix is the division of number. Okay? Now. Okay. Now what? Let's see what is it. So, let the complex number to be the set of all matrix of the following form. See? I make matrix, I don't make vector. Because the black vector I cannot multiply to vector. So I put 2 matrices, I can multiply 2 matrices. You can see, it looks like the same. So this is the question I asked professor in the math department. They teaching complex variable. And I asked them, what difference between this plane and the other plane? It's the same. But what is the difference? The difference is on algebraic property. You can see, if you look at the qubit, you look at the qubit, when alpha is a complex number, okay? It's just like, if you write out alpha like xy, then you cannot multiply. Because this is the vector. This is the vector 1, 0. So if you write alpha like this, you cannot multiply. But if you write out alpha equal x plus iy, then you can. Because it's a number. Then you can multiply a number because the vector is really a vector space. So if you're doing that, look at C. What is it? What is it? This can be written as x 0, 0 plus 0 minus 1, 1, 0. Let me see if I. Okay. Is that what I exactly? Right. Okay, is that correct? You can see. Okay, let me multiply the 2 matrices first. Okay, you multiply these 2 matrices. What do you get? Multiply the 2 matrices. Okay, so you get 0. Okay, here you get y, right? Let's see. Okay, this one 0, I get 0, and then the second one I get y, and then 0. 0, I get minus y, and then over here I get 0. Okay, that's 0, and 0 becomes 1, and 0 y. Okay, that's correct. So this one is this one. And this one, when I multiply, I get 0. That's 0. And
that's y.
Now I add them up. So I get x minus y, and y. Let's see. Okay, I get. Y, and I get x. That means I have that. Okay? Okay, now, what is it? This is a number in here. This is a number in here where x is equal to 0 and y equal 1, right? Okay? So this is the number in there. Let's square it up. What do we get? Okay. X minus 1, right? And we get 0. And I get 0. And we get minus 1. Right? Now, this one is equal to x, right? That's what identification. This one is equal to y, and this one, call it I, and I square equal minus 1. Nothing fancy. It's not just, oh, imagine some number I and I square equal minus 1. No, it's a metric. Precisely what it is. Okay. Because this metric is identified with a minus 1. Exactly like here. You have 0, 0, and what is x? That x, this is the number x. And here, that number x is minus 1. And this is the number I. The number I. So, only metric is enough for everything. I start from only, you know metric, you don't need to know complex number. Only metric, you know everything. So from now on, C is called a complex plane. It is a plane, it's the same thing. But the operations are different. They act like a number. You can multiply, so you can divide. You can divide equations. It is the inverse of the equations. Look into that, you can see all of them. Okay? So every number in here, called it C, is of the form x plus iy. You know what is I now? That matrix. You can operate like a number. You write x, y, you cannot multiply. When you write like this, you can multiply. Okay. That is why we were doing that. And the complex conjugate, that notation, and you just change the sign. The absolute value of the one is simply what is that? Just like a multiply, we will write x. That's just like a Pythagoras one. So we will call this the norm. In quantum, they will call the norm. move ahead in a minute. Human space. Now, 1 minute. Okay. Now, time enough just to introduce one more thing, then we continue next time. Let's take C2. This will be the state space of 1 qubit computer. Is a Hilbert space. Attention, number one. You know exactly what it is. No need of talking about Hilbert and why you need to. The space of Newton is the Euclidean space of dimension 6. The state space of a quantum system is a Hilbert space. What is the difference? Okay, let me tell you this. Hilbert space. Just like quantum, don't be scared of the word Hilbert. In fact, you know very well. This is in the first course in the PhD program here. Remember, we have Hilbert space, then we have Banach space, we have separation of convex set and things like that. It's all more than enough for you to understand quantum mechanics in that first course here in Cornell 07. So why we need? Because we need, first of all, what is it? This is a set of vector of dimension 2 of the form of vector, but the components are complex number. That constitutes just like R and R2. Okay? Okay? Everything we do is if you have a real number, one is R2, Cartesian product, that's what you have to plate. Now you just replace real number by the plate, the complex number. And you replace R by C2. So if you want respect to R is dimension 4, okay? But we're talking about complex, so dimension 2. It's a vector where the two components, but the components are not real vector, real number, they're complex number, okay? So that is the state space. So if that is all that we do, so why we need to talk about Hilbert space? And why? What is special about Hilbert space? Hilbert space, we can talk about deep without of the world. Only on Hilbert space that you can talk about that. They are vector space, but it's very special. And why? Because they have inner products. And you will see, oh, they have everything here. You can define Hilbert space. What is this? What is the if you have two vectors like this, if you have two vectors, if you have what is the let's say this is one, and what is, okay, I will write down this notation for you. Inner product side. Another one. Okay. What is it? Okay, so this is, remember if you have x equal x1, x2, and y equal y1, y2, then the Cartesian product of these two vectors is summation of x j y j. Let's say. So here, just think about this one is this one, but only the fact that they are complex. So in complex, in order to make this into you have to replace this by the conjugate. That's all. Replace by the conjugate. Then you can do. Now, we say two things on this. It has, when it has inner product, you can talk about projection, orthogonal. But why projection? Why projection? What we need projection in quantum computer? Everywhere. That is the way to measure. To measure it. You send in the qubit. You don't know what it is. You only know the form. You only know the qubit is like this. What does that mean? There are two things that it can be. Think about this like a quantum. This is like you have a quantum coin. Okay, it has one head and let's say call it tail. Okay. And the probability of this getting this is alpha square and beta square. It does not go. But the difference is this. When you toss it, you cannot tell it's head or tail. You have to measure it. That's the difference between ordinary statistic and quantum statistic. Ordinary statistic, if I ask you how much you make a month, you tell me that you give me exactly what I want. I don't need to do anything else. I observe. Okay? What is the temperature in Chiang Mai yesterday? I should look at the thermometer and I see it. 35 degrees. I don't have to do anything else. But if you want to figure out, let's say, what is the electron running into the electricity, you have to do something else to find out. You cannot see. You cannot observe. And that's exactly what happened in the qubit. You stand in the qubit, you know it's like this. But you don't know 0 or 1. How to find out? Projection. That is the only way to do measurement. We project that state on the axis. So let's say you call this the axis 0. Okay. So next time we will talk about speed. Okay. The electron can have speed. So if you want to know it is in this direction or in this direction. Think about this. This is a qubit. It's there. It doesn't tell us where it is. But it can only be this or this. So how we find out it? Orthogonal. And that only possible with the space is Gilbert. Who is Gilbert Space? I will tell you quickly. He is the advisor of von Neumann. John von Neumann, he is the one who write out the mathematics of quantum mechanics, the foundation. And his teacher is Gilbert. And Gilbert is a mathematician. Gilbert doesn't know anything about physics. He just do that for fun. Okay, there's a space, Euclidean space of finite dimension, why not infinite? He just do it for fun. But it turns out that is exactly the math, the new math that von Neumann did to study the new mechanics of the 20th century. So let me just give you an idea. We need Hilbert space because we need to be able to talking about auto-load protection, because that is the way to figure out, just like for quantum computer, for example, you send in something, if you want to get out something that you did, we will do that next time when we talk about the game, when we want to create and tackle a thing or so Hilbert space. And also the second one is very important. We are not talking about 1 qubit. There's nobody build 1 qubit computer. We are using several qubit computer, like a 3 or 5 or 20. Now think about 3, for example. 3. So the first thing to talk about algorithm for that one is what is the state space of the quantum computer. So 1, you have that. 5, because it is Hilbert. You can measure. Now you have another one. Coupled with this will become a composite system. What is the state space? Not the Cartesian product. It will be a tensor product. We're talking about that next. Why? Again, one more thing. Anything that I cannot explain, I will say, go to the physics department and ask. That's the physics. Okay? We have to trust that. Why? Because you have your iPhone. More than successful. More than anything else. Okay? Even people still don't know is that correct or not. Okay? But it's so successful. So that is more than enough. That is more than enough. So if you have two qubits, this will be the state space. And it is not a Cartesian product. It's what we call the tensor product. But when the tensor product, so the question is, these are the Hilbert. And every state space has to be a Hilbert space. If it's not a Hilbert space, you cannot find out the apparatus to measure what you want to see. If you don't know what happened, you cannot do anything. Just like we gather data. I asked him a question. How much you make a month? Okay? I need to know the number. So he just tell me that all I need. I don't want to do anything. But here, the thing we send in very efficient, but they are so weird. We have to leave it. So in order to find out what it is, we have to make a measurement. And then we will see what is more important. And when you do that, you will disturb the state. Okay, so I think that we got time. Okay, so this is only the first 7 pages of my handout, and the rest I think you have here or you have to read it.
The copy, right? Yes.
For everybody?
Just 5, but some of them have already. But some of them that don't have, I said there.
Okay. One good thing, if you want, is could you put a piece of paper and put everybody, put down the email. Put down your email, then I can send to everybody. Yeah. And, okay, so okay, this is, I thought I can go more than that, but everything I said, everything like this, okay? The rough measure of everything, every symbol, everything will be explained completely, and it's in here. Yeah, write out clearly, yeah, nicely the emails, so I can send everything. I can send everybody everything from A to Z. I write out in such a way that you should not only understand easily, but you should enjoy. Okay, Ajahn, everybody, questions? Questions? No, you have to understand everything I said. If you don't understand, you have to ask now. Anything, I need the picture very clear. We simply okay, I will send out. Yeah, I will send the handout for you. Yes. I hope so. Any question? I need one question for each person. No. I mean, because I spend a lot of time and write down things. Hopefully that I don't let any stone unturned. Okay. Okay. Yeah.
Maybe it's not question, but I think next time we may pay more attention on tensor quantity. I think it's fundamental. So many of them may not have an idea what is tensor.
Tensor product is not the name. What is the tensor? Stretch. Tensor means tension, stretch. Tensor product is a stretch out product. That means you have a vector of dimension 2. You stretch it into dimension 10. It's called the tensor product. You multiply two vectors. You multiply two vectors to get a bigger one. You don't need, first of all, okay, you don't need to call it tensor product. Huh?
You then need to know the tensor quantity.
No, it's, everybody knows because that's Kronecker. Let me tell you, you don't need tensor. Tensor because they write tensor, so I write tensor. Tensor product only when the dimension is infinite. But we do computer, we don't have infinite. We have a finite. The space space of quantum computer is C to the n. Tensor product of two matrix. You have two matrix. Okay? You have a matrix AJK. Let's say dimension M plus N, and you have another one. Anything you like. Speaking different. Can you multiply? Can you multiply two matrix like this? No. This one have to be equal this one if you want to multiply two matrix. But you can. If you stretch. This is called Kronecker multiplication of matrix. What is that? You spread it. Okay. A11 time a week. A21 time a week. M1 week. Huge. You start out like that. So let me give you quick an example for C2. Okay? Over here, what is that? You have one vector which you write down like 1, 0, and the other one you write down like 0, 1. Okay? Now when you have two of them, so what is the tensor product of this one with itself? That is the huge vector straight out. This one, so it's 1, 0, 1, 1, 0, 0, 1, 0. And that is vector of 4 dimensions. 1, 0, 0, 0. Okay? That just we multiply by canonical. Okay? So that is, and this one, we write 0, 0. That's what is the language that we go into detail about that.
Okay. I'm not sure that I understand that correctly or not. In the cubic case, it's like let's say that when we have a cubic and we want to observe it, we use the product, right? To measure.
Yeah.
Right.
Yeah.
So when we represent one cubic by is vector of C cube, right? And then when we observe them, when we measure them, we use inner product, then is it like in the case in the whiteboard that we choose y to be, let's say 1 and other thing is like y, and then we project.
When you send it in, when you see it, you send like this. You decide alpha, you decide beta, and you say that you want to prepare. Okay, you send it in. The machine will do something, depend on what to do. We will see. Go through the Harama gate, we go to the NOT gate, go to the square root gate, you will be, and it come out one cubic. Okay. You want to know is 0 or 1. Okay, so if you want, so first you project on 0 instead of not. Okay?
And by project to 0, serious. 0 here is two-dimensional plane, right? It is complete.
But the 0 in the vector, the basic vector is 1, 0. It's the inside C2. It's a real, but it is the same unit as R2. Okay? So you project on it, and we will talk about what is projection. How you make the projection. That's what everything linear operator or it's nothing else. Matrix is a transformation. We change the vector to another. So the gate will be transformation, and projection is transformation. Everything is transformation. And here, no question means you understand everything. I don't know. I don't know. I don't understand why so difficult. Because just take analogy of a computer that we don't make. We don't care. No, we're talking about quantum physics, maybe something weird. But in respect to quantum computing, we have something very easy. You have to know quantum computing. You don't view the machine, but at least you know what it is. You know the logic is moving logic. In order to do the operation, you have to put, first of all, you only have 0 to put in. You can have a string of 10, 0, 1 that used for coding, only number you do. Okay? You prepare that one. You want to put number 5, you want to 5 plus 7. You want the machine to do for you because you don't want to do by 10. Okay? So how do you put in number 5? You already have the convention that 0, 0, 1, 1 is 5. Because you can only put in 0, 1, you cannot put number 5. Because the machine can only do the voltage. If the voltage is like this, above this one, you call it 0. Below that, you call it 1. So the machine, the electricity can only do 2 things. Okay, so you input it in. Inside the machine, well, you give interaction. Okay, what to do? But the machine is universal, so it can execute inside a gate. Gate means what? Changing one thing to another. That's called a gate. You go through a gate. And all the gates are built by only 3 operations. Union, intersection, and NOT. So they have that called Boolean logic. Okay? So you go through that and get out for you the output. The output, you don't have to do anything. because the computer memorize. If you see come out number 0000 and oh that number 7, it put out for you 7 because they memorize that. Okay, you don't have to do anything. Now you have to do something because so good, but better than that. It's a little bit more. The difference is the thing you come in is not to give 0 and 1. When you say, let's say a 5 qubit, whatever you have to understand. So that's what I try. It's not trying to really explain that. I try to explain the language, mathematics, symbol, operation that I use to do that. But the rest is very similar. Rather than put in 0, 1, you put in something else to replace. Inside the machine, that's what they will do for you. They will have quantum gate. Okay. They have a gate called square root of naught. They will have. And the question is, why they have to do that? In order to get something better, you have to work a little harder. In order to get something quick and fast and things like that, you have to create something. One of the things I just mentioned is that we need to create an angle system. Because that will make speed up the computer. So how you make that? You send in an ordinary one. You send it, let's say you put in 2. You want to have to correlate it. Because that's good for you, for computation. You want to put them through again. You want to make again. So when they go through, when they come out, they change and correlate it. Okay, so all that one, the mathematics, the language, the thing of, and that's what we try to cover. And I think that only next time if I go from beginning to the end, without the introduction, it will go away everything. If I get the list of email, or you ask, I say, well, because you better, it only take you better read before next time. And this one, it will take you not that 1 hour, everything. So I write that. So after that, you can say, oh, it takes me a long time from 0 to this. Okay. All of this. Today, I just covered only the first thing, only the complete number. Okay. So I just start the Hilbert space for CS. And all the way until okay, the part 2 is after. All the way until you can create entanglement. That means after all this one, you are done. That means if you look at the quantum algorithm, you can read and understand all the symbol and all the what you make. When they say, go to tensor product, you know what it is. Okay? So, and then if you look at, what we did, if you look at this book, okay, if you look at this book, I think that we said it a long time ago, nobody printed it out. Okay, if you look at chapter 8, quantum algorithm. Take you about 1 hour to read, and you understand everything. No need of way or anything. Everything is given from A to Z. What is the speed? The speed because what is the speed? What is the line polarization? And how they do it? It's clearly for you. How you prepare the qubit to put inside. Anybody good in computer, it's easy. It's just everything is just similarly, but instead of putting tables like this, to do something a little more complicated. And no need of math. As I said, you don't really make it. And in fact, you don't manipulate it. Okay. You don't need to manipulate it. You only need to see photoneutralization. How you put the light in order to come out to different color. And you rotate to different rotation of that is a projection. The projector. See? Everything. I think it's very effective. And, so there are two other books. All of them are available to see. If you want to get into actually how to do that, what are the algorithms existing, and what are the computer that you can do. Can you run a quantum mechanism on ordinary computer? What is quantum annealing that we have here? On that one, okay? One is it's just like that. One, you know, you are not doing the algorithms. You just learn how to read the algorithm and apply. And after that, like how to create the input result. So we will. Okay, if no question, okay. So you will send out to them. You will provide them to have.
Yes.
Okay, send everybody. Everybody have it.
They have already.
Okay.
They have the data file already.
Okay. So it's good. It's good if you read before and then after, because I really want to make sure that you understand everything. I go over. I just there that anything that I did not cover. Okay.
Okay, so this is our first seminar for the quantum computing that for the course. I hope that you might get something, at least get something, not get off. I know that it's quite difficult to get everything, but you have this one already. And today I will send this book to all of you. It's pretty simple. It's not mathematics book. It's just explanation, everything is, but very few mathematics. I believe that if you cannot understand this one, you can look at this textbook. And today's class, we focus only the qubit only. Okay, we not go to the gate yet. We not go to the output yet. But go only in the qubit stage. Okay, so I hope that at least all of this hour that this in these 2 hours, I hope that you can understand a bit about what is qubit and how we build the qubit, right? It's a wave, right? And how when we find the qubit, Professor mentioned about the wave function already, and he asked us to learn about the complex number in order to understand alpha and beta, and he showed the matrix that how and why we have to make that notations, because you cannot multiply the vector, right? Cannot multiply. That's why we need the complex number in order to multiply the vector that we multiply. So that's the idea first. But I know that this is a bit tough and it is quite new for you, but at least you get some meaning. Okay, I hope. Okay, so
And you can make sure that you can read and ask questions on that next time. Okay?
Yeah.
Read that carefully. I hope that everything in there. What is missing? What is not clear? What you need to know more? Don't forget. Don't ask the question. How I run the algorithm? Okay, that is after. Okay, but read all of this and ask questions about that. So we will next time, next year, next week, not next life. Next week, same time.
So the next seminar will be held on next Wednesday, and the room may be this room or the seminar room. But I will inform later in the poster. And then I will give this book to you. Okay, this is for the beginner. Okay, I hope that you learn. Okay. By the way, thank you so much.
Okay. So the next week is the rest. Over the rest of the handout.
You want to go back in the red one.